The boundary between survival and destruction is often defined by a single mechanical lockout. On December 17, 1944, the crew of a consolidated B-24J Liberator found themselves trapped on the wrong side of this line. They were circling above the Adriatic Sea with the island of Vis visible through the cockpit glass. They still had fuel. They still had altitude. They had reached the designated emergency field, but they could not touch the ground. The heavy bomber was caught in a terminal paradox where the aircraft could still fly, but it could no longer land. The machine in this sequence carried a serial identity on the books. On the registry, it was just another B-24J, indistinguishable from thousands of Liberators by pure specifications alone. But it did not come from a generic production line. It carried a provenance that followed it from the factory floor into combat. This specific aircraft was the final B-24 produced at the Douglas Aircraft Company plant in Tulsa, Oklahoma. Its story was tied to a war bond drive championed by the factory workforce. The workers signed their names and messages of support directly onto the aluminum skin of the fuselage before it was painted. The crew knew it as the Tulsamerican. The aircraft was on a long-range strategic mission targeting oil refineries near Odertal, Germany. It was approximately mission number 151 for the group. Near the target area, the formation was intercepted by Luftwaffe fighters. The engagement resulted in catastrophic damage to the hydraulic system of the Tulsamerican. In a B-24, hydraulics drive the critical mechanisms, most importantly the landing gear. Without pressure, the wheels cannot be lowered and locked with any confidence. Over Vase, Lieutenant Eugene Ford shifted to the emergency procedure. The crew began the manual extension, a slow, labor-intensive grind that demands steady flight long enough to force the gear down and verify the lock. Ford held the bomber in a wide circle, trading fuel for time because a runway was still safer than putting a 30-ton aircraft into open sea. Now everything depended on whether that manual effort could finish before the aircraft ran out of margin. However, the damage from the German fighters was not limited to the hydraulic lines. As the aircraft circled, one of the 4 engines lost power and failed. The B-24J is a high-drag airframe. With 1 engine out and the remaining 3 under strain, the aircraft struggled to maintain airspeed in a turn. The loss of thrust created an immediate asymmetry. The pilot could no longer maintain the altitude required to finish the manual gear extension. The operational window slammed shut. The aircraft was now too low and too heavy to regain altitude on the remaining power. The decision was no longer about landing, it was about controlled impact. Lieutenant Ford had to abandon the runway approach and commit the aircraft to the surface of the Adriatic. The crew of 10 men braced for a collision with the water. 7 of them would escape the fuselage. 3 of them, including First Lieutenant Eugene Ford, were killed in the ditching, and their bodies could not be recovered at the time. In those seconds, the Tulsamerican stopped being an aircraft in motion. It became an unanswered record, sealed off by water that kept its last mechanical failure out of reach. The ditching ended the flight, but it also opened a new timeline, one defined by what could not be seen and what could not be recovered. To understand why the crash broke the Liberator the way it did, you have to look at what it was built around. The consolidated B-24 was designed around a specific aerodynamic component known as the Davis wing. This airfoil utilized a high aspect ratio geometry, meaning the wing was long and narrow relative to its chord width. In the air, this design reduced drag and generated exceptional lift, allowing the Liberator to carry heavy payloads over long distances with greater efficiency than its contemporaries. However, the engineering trade-off for this aerial efficiency was a distinct structural fragility when subjected to off-axis loads. The Davis wing was optimized for the fluid dynamics of air, not the high-density resistance of water. When Lieutenant Ford committed the Tulsamerican to the Adriatic, he entered a regime where these physics turned against the airframe. Ditching a heavy bomber requires a precise angle of attack to skim the surface. But the B-24 features a shoulder-mounted wing attached to the top of the fuselage. Upon contact with the sea, the fuselage strikes first, acting as a hydroplane. If the nose digs in, or if the wings catch a swell, the deceleration forces transfer instantly to the wing roots. The impact energy of a 30-ton object hitting water at roughly 100 miles per hour is not absorbed. It is converted into structural deformation. Water at these velocities behaves less like a fluid and more like a solid concrete surface. The Davis wing spars, designed to support the weight of the aircraft from below during flight, could not withstand the massive shear forces generated by the sudden deceleration of the fuselage in the water. The structure failed. The fuselage buckled and broke apart under the strain, snapping the integrity of the crew compartments. This breakup sequence is the primary reason the loss became a fatality event rather than a total evacuation. The structural collapse inverted the aircraft. The Tulsamerican rolled upside down almost immediately after impact. This inversion disoriented the crew and submerged the escape hatches. 7 men managed to exit the broken fuselage as it flooded, fighting against the sudden inrush of the Adriatic. 3 men positioned in the forward flight deck and the nose turret were trapped inside the collapsing structure. The wreckage did not remain on the surface. Deprived of buoyancy and weighed down by the engines, the inverted forward section sank rapidly. It descended through the water column and impacted the seafloor at a depth of 41 meters. The tail section, severed during the breakup, drifted separately and came to rest in deeper water. At this depth, the environment shifts from a dynamic crash site to a static preservation chamber. The energy of the crash dissipated, leaving the aluminum skin to settle into the sediment. For the 7 survivors floating on the surface, the event was over. For the 3 men inside, the fuselage became a sealed compartment at the bottom of the sea. The depth of 41 meters places the wreck beyond standard recreational diving limits, complicating any potential recovery and demanding careful planning. It was no longer an aircraft in any practical sense, only an underwater evidence field breaking down under the slow chemistry of salt water. Whatever happened to Lieutenant Ford and the men trapped forward was sealed inside an upside-down metal shell, buried in silt and out of reach. For 65 years, the location of the aircraft remained an unresolved coordinate in the history of the unit. It was not until December 2009 that a team of divers located a concentration of aluminum debris off the coast of V's. They had found a crash site, but in a theater of war littered with downed aircraft. Finding debris is not the same as finding the target. Confirmation required a specific evidentiary signature. On May 31, 2010, divers recovered a corroded metal data plate from the wreckage. Cleaning the artifact revealed the stamped nomenclature. The serial number read 42-51430. This number provided the absolute link between the underwater debris field and the factory floor in Tulsa. The identity of the wreck was verified. The Tulsamerican had been found. However, the environment protecting the wreck presented a significant operational barrier. The site sits under a decompression ceiling. Stay too long on the bottom and a direct return to the surface becomes physiologically impossible. On standard air, working time collapses to minutes before mandatory stage stops are required on ascent to prevent decompression sickness. That time constraint makes traditional manual survey methods inefficient. A diver cannot simply hover over a wreck with a tape measure and a clipboard when the nitrogen clock is ticking. To overcome this nitrogen constraint, the survey team utilized a technique known as photogrammetry. This process replaces physical measurement with optical reconstruction. Divers swam a rigorous grid pattern over the wreckage, capturing thousands of high-resolution still images from multiple angles, each overlapping with its neighbors to create a dense dataset of reference points. Computer software then analyzed these reference points to reconstruct the geometry of the wreck in 3-dimensional space. The result was a high-resolution digital model of the site, created without a single diver needing to touch the corroded metal. On a surface monitor, the team could read the fuselage's attitude, upside down, the flight deck pressed into sediment, and trace the positions of engines and fragments across the scatter radius. The photogrammetry survey delivered what debris alone could not: a clear orientation, a usable map, and a planning-grade view of what was still intact. But the digital model could not see through the sediment packed into the cockpit. It could confirm a wreck and map its shape without disturbance, but it could not answer the only question that mattered: whether the missing crew were still inside. Sonar and magnetometers can outline aluminum and flag iron. They do not provide positive identification of human remains. Closing that gap meant ending observation and beginning excavation, breaking the seabed seal and physically entering the wreck. In June 2017, the Defense POWMIA accounting agency initiated a full-scale recovery mission on the Tulsamerican. The objective was to excavate the sediment-filled nose section of the inverted fuselage. The primary constraint was time on the bottom. The divers were working under decompression limits that turned delicate excavation into a race against physiology. Every minute spent working the wrong patch of sediment was a minute lost. To manage that constraint, the team worked within a forensic grid, documenting finds by precise position as the site was cleared. Removing decades of accumulated sediment required controlled underwater excavation methods designed to move bulk material without destroying fragile evidence. Spoil was recovered and screened so that small artifacts or osseous material could be isolated and documented. Inside the crushed nose of the Liberator, the excavation team encountered a dense layer of debris. Mixed among the aluminum ribs and control cables, they discovered a mass of fabric, parachute material preserved in the low oxygen mud. Clearing and documenting that fabric opened access to what lay beneath. Beneath the parachute material, the divers recovered evidence consistent with their objective, including possible human remains and associated items from the cockpit area. In an open ocean environment, currents can scatter light material and complicate separation and identification. Here, the sediment held the evidence, the grid mapped it, and the excavation revealed it. The team was no longer just moving mud. They were recovering what the sea had hidden for decades. The output of an underwater recovery mission is rarely a complete skeleton. It is a collection of fragments separated from the debris field and isolated in a laboratory environment. When the screening baskets were hauled to the surface from the Adriatic, the contents were a chaotic mixture of Adriatic sediment, aluminum corrosion, and biological material. The distinction between a successful recovery and an indeterminate survey lies in the ability of the forensic pathologist to extract a specific identity from this mass of evidence. Among the material isolated during screening, the team recovered personal items consistent with an aircrew station. In the context of a blind crash site, personal effects can function as secondary identifiers. A serial number plate identifies the machine, but the small details of equipment and personal property can help investigators narrow the question of who was where before laboratory science delivers the final answer. Personal effects can be suggestive, but absolute proof requires biological matching. The osseous material recovered from the seafloor was transported under a strict chain of custody to Department of Defense laboratories. Here, the investigation shifted from the physical constraints of diving to the chemical precision of DNA analysis. Scientists from the Defense POWMIA Accounting Agency and the Armed Forces Medical Examiner System compared the samples against reference material provided by surviving family members. The science confirmed what the excavation context had suggested. The remains were positively identified as those of the pilot. This identification closed the open loop for First Lieutenant Eugene Ford. The recovery of his remains validated the decades-long wait and the expense of the deep water operation. But the outcome of the mission was not a full accounting of the crew. The ditching left 3 men missing. The excavation could identify the pilot, but it did not fully recover the other 2. Navigator Russell Landry and flight engineer Charles Priest remained unaccounted for in the initial release of these findings. The decision to terminate a recovery operation is driven by the same limits that shaped the search. Once the accessible sediment in the flight deck and nose positions had been cleared, and depth, weather, and time had been spent, the mission reached its practical edge. What it returned was not a complete accounting, but it was not nothing. One named answer recovered from a general loss. The recovery proved that the site was not just a wreck, but a repository of retrievable evidence. It demonstrated that even after 7 decades of immersion, an identifiable biological signature could still be isolated from the ocean floor. The return of an identified serviceman to his family marked the end of the forensic process for one officer, but it highlighted the reality of the 2 names that remained on the missing list. The mission had achieved its primary objective of identification, proving that the technology exists to reach back into the timeline of 1944, provided the specific location of the evidence is known. The preservation of a submerged aircraft is determined by a chemical countdown that begins the moment the fuselage enters the water. While the depth of the Adriatic protects the wreckage from surface wave action and ultraviolet degradation, it subjects the airframe to relentless galvanic corrosion. An aircraft is an assembly of dissimilar metals. The skin and ribs are aluminum alloy, while the engines, landing gear struts, and control cables are hardened steel. When these materials are connected electrically and submerged in a conductive electrolyte like seawater, they form an unwanted battery. In that reaction, the aluminum tends to act as the sacrificial anode, giving up material to protect more noble metals. Over the course of 73 years, this process can attack structural elements and fasteners, loosening skins and weakening joints. But the pace is not fixed. It rises and falls with local conditions, oxygen, currents, temperature, and the way metals contact each other, silently rewriting the wreck year by year. It ensures that the wreck of the Tulsamerican is not a permanent monument but a disappearing resource. The window to read the history stamped into the metal is closing. This dissolution erases more than engineering. It strips away the aircraft's one-of-one backstory. The Tulsa-built Liberator the workforce paid for, signed, and sent to war under a name of its own. Those personal messages are among the first details to disappear, fading as corrosion turns a specific identity back into anonymous debris. With the recovery of the pilot and the positive identification of the airframe, the operational status of the wreck changes. The site is no longer an active forensic crime scene. It transitions to a phase of site stabilization. In the context of underwater aviation archaeology, stabilization does not imply repair or restoration. It is a strategy of non-disturbance. The goal is to allow the wreck to reach a chemical and physical equilibrium with the sediment, slowing the decay by preventing human interference. The Tulsamerican is treated as a sensitive military loss site, and for many, a potential war grave under Croatian jurisdiction. That status creates a boundary around the debris field, discouraging disturbance and tightening expectations of respect and oversight. This protection matters because the wreck still holds the potential remains of the 2 unrecovered crew members. The site is not empty, it is simply silent. The recovery mission of 2017 reached Lieutenant Ford before the sea could erase him. It retrieved the necessary evidence while aluminum was still holding together and before the cockpit disappeared under another generation of silt. The physical aircraft will eventually succumb to the Adriatic, reducing to steel engine blocks and rubber tires on the sand. But the historical loop has been closed. The workers in Tulsa built the machine to carry the war to Germany. The machine failed, but the commitment to the crew did not. The return of the pilot's ring and the documentation of the site ensure that even as the metal vanishes, the record of the final flight remains permanent.